The universe is so big that even the fastest thing we know, light itself, takes billions of years to cross it. The wildest part is that we're only seeing a fraction of what's actually out there. So today, we're going from our tiny little planet all the way to the edge of everything in 7 levels. Level 7, the solar system. Level 7, the solar system. You already know the basics. Earth orbits the Sun about 93 million miles away, a distance light covers in roughly 8 minutes. Our planet has oceans covering 71% of its surface, 8 billion people walking around on it, and mountains like Everest reaching 29,032 feet high. The Pacific Ocean alone is wider than the Moon. From up close, Earth feels massive. Every canyon, every coastline, every thunderstorm seems enormous when you're standing in it. But zoom out even a little, and Earth becomes a dot in a much bigger neighborhood. The solar system goes way beyond the 8 planets, past Neptune, which orbits at about 30 astronomical units from the Sun. Where 1 astronomical unit equals that Earth to Sun distance, you reach the Kuiper Belt. It's a donut-shaped ring of icy rocks where Pluto and a bunch of comets live. Pluto, by the way, got reclassified as a dwarf planet back in 2006, and it sits right in this region. But keep going past the Kuiper Belt and things get really empty and really big. The Oort Cloud is a gigantic spherical shell made of trillions of icy objects. Its inner boundary starts at around 2,000 astronomical units out, and its outer edge stretches to 100,000 astronomical units or more. That's about 1.5 light years from the Sun. Light from our star takes over a year just to reach the farthest parts of our own solar system. If you were standing on one of those frozen rocks at the edge, the Sun would look like any other dim star in the sky. You'd have no idea which one was yours without a map. Here's a way to make this click. Shrink the Sun down to a basketball and place it in New York City. At that scale, Earth would be a pea about 100 yards away in Central Park. Jupiter becomes a grapefruit roughly a mile out in Midtown. Neptune is a cherry 2.5 miles away near the Hudson River. And the outer edge of the Oort Cloud at that same scale would be all the way out at the Moon, over 238,000 miles from Earth. That's how enormous our backyard is before we even leave it. The distance between planets feels big when you read the numbers, but when you map it onto something real, the emptiness between everything becomes almost hard to believe. Voyager 1, which NASA launched in 1977, is the farthest human-made object from Earth. As of 2026, it's about 164 astronomical units away. That sounds impressive, and it is. Voyager has been flying for nearly 50 years, and it'll still take another 300 years before it even brushes the inner edge of the Oort Cloud, and roughly 30,000 years to cross it. We've barely stepped off the front porch. Level 6, the Milky Way. Our galaxy is a barred spiral stretching about 100,000 light years across. It holds somewhere between 100 and 400 billion stars. The Sun sits in one of the spiral arms called the Orion Arm, roughly 26,000 light years from the galactic center. Right at that center sits Sagittarius A star, a supermassive black hole with a mass equal to about 4 million suns. Everything in our galaxy, including our entire solar system, orbits around this black hole. To get a feel for the Milky Way's size, if you could somehow drive across it at 60 miles an hour, the trip would take about 100 billion years. It's more than 7 times longer than the universe has even existed. Light, traveling at 186,000 miles per second, still needs 100,000 years to cross from one side to the other. Our solar system's moving through the galaxy at about 514,000 miles per hour, and at that speed, it takes roughly 230 million years to complete a single orbit around the center. Astronomers call that 1 galactic year. Since the dinosaurs went extinct about 66 million years ago, Earth has completed roughly 20 of those galactic laps. Every time our solar system finishes one orbit, the planet looks completely different from the last time around. Continents shift, species appear and disappear, and entire ecosystems get replaced. And here's the one thing about stars. There are so many in the Milky Way alone that if you counted one per second, Non-stop. No sleeping, no eating. It would take you over 3,000 years just to reach the low end of the estimate. You would die thousands of generations before you finished counting, and keep in mind, the Milky Way is just one galaxy. There are at least 2 trillion more out there that we know of. The number of stars in the observable universe is estimated around 200 sextillion. That's 2 followed by 23 zeros. And just let that number sit in for a second. Level 5 superclusters. Level 5 superclusters. The Milky Way is part of a group called the Local Group, which is a collection of around 50 galaxies spread across 10 million light-years of space. Our closest big neighbor is the Andromeda Galaxy, sitting at about 2.5 million light-years away. Andromeda is heading towards us at around 250,000 miles per hour. In about 4 billion years, the two galaxies will collide and eventually merge. That sounds catastrophic, but galaxies are mostly empty space, so individual stars almost never actually crash into each other during a merger. The night sky would change dramatically over millions of years, though. 2 entire galaxies slowly blending into one. New star formation would spike as gas clouds compress, and the combined galaxy would eventually settle into a giant elliptical shape. Astronomers already have a name for it: Milkomeda. Now, zoom out more. The Local Group is part of something much larger called the Virgo Supercluster. And in 2014, astronomers discovered that even the Virgo Supercluster is just a small piece of an even bigger structure they named Laniakea, which is Hawaiian for immense heaven. Laniakea is a web of over 100,000 galaxies stretching across 520 million light-years, with a total mass of about 100 quadrillion suns. Everything in Laniakea is being pulled by gravity towards a dense region called the Great Attractor. Nobody can see the Great Attractor directly because the plane of the Milky Way blocks the view with dust and stars, but its gravitational influence is measurable across hundreds of millions of light-years. Here's where the scale really hits. If Laniakea were the size of a human body, the entire Milky Way galaxy, with its hundreds of billions of stars, would be about the size of a single atom. And Earth, with every mountain, every ocean, every city, every person who's ever lived, would be smaller than a red blood cell floating somewhere inside that body. A human red blood cell is about 7 micrometers across, smaller than a speck of dust. Scale Earth down to that size and the sun becomes a beach ball 100 feet away. The entire solar system fits inside a football stadium. The Milky Way becomes a disk the size of North America, and Laniakea spans the entire continental United States with galaxies scattered across it like grains of sand. Carl Sagan, the famous American astronomer, once said we are a way for the cosmos to know itself. When you see where Earth sits in just this one supercluster, that idea hits differently. Level 4, the observable universe. Everything we can detect with our telescopes forms a sphere centered on Earth, and that sphere has a diameter of about 93 billion light-years. You might wonder how that's possible when the universe is only 13.8 billion years old. The answer is expansion. Space itself has been stretching this entire time. Light from the most distant objects started traveling towards us 13.8 billion years ago. Those objects have been carried even farther away by the expansion of space since then. So, the actual distance to the edge of what we can observe is much greater than 13.8 billion light-years. Inside this observable sphere, there are roughly 2 trillion galaxies. Each one contains billions of stars. Add all those stars together and you get a number larger than the total grains of sand on every beach on Earth. To put that in perspective, scientists estimate there are about 7.5 times 10 to the 18th grains of sand on Earth. The number of stars in the observable universe is at least 10 times that. The farthest confirmed galaxy we've seen is called GNZ11, observed by the James Webb Space Telescopes at a distance of 13.4 billion light-years. We're seeing it as it looked just 400 million years after the Big Bang. That galaxy no longer looks like that. Over 13 billion years have passed since that light left. Whatever GNZ11 has become, we'll never know, because the light showing its current state hasn't had time to reach us yet. and the observable universe is almost certainly only a fraction of the full universe. The total cosmos could be infinite, or at least vastly larger than what we can see. There are theories about multiverses and regions beyond our cosmic horizon that light has simply not had enough time to reach us from. Some 2026 research has even raised the possibility that the expansion of the universe might eventually reverse. If dark energy, the mysterious force driving expansion, is weakening over time, the universe could eventually enter what physicists call a big crunch, where everything collapses back in on itself. That's still heavily debated and nothing is confirmed, but newer data from missions like the Dark Energy Spectroscopic Instrument, known as DESI, is giving scientists fresh numbers to work with. The question of whether the universe expands forever or eventually falls back inward is one of the biggest open problems in all of physics right now. Think about the balloon analogy for a second. An ant crawling on the surface of a balloon only knows two dimensions, forward and sideways. As the balloon inflates, every point on its surface moves away from every other point. There's no center of expansion on the surface and no edge the ant could ever reach. The ant could walk forever in one direction and never find a wall. The surface is finite, but it has no boundary. Our universe works the same way, just in 3 dimensions instead of 2. Space is stretching everywhere at once, and there is no center and no edge to find. Level 3, Cosmic Mysteries. Before we get to the telescopes, there are a couple of wild ideas worth knowing about. Cosmic strings are hypothetical, ultra-thin cracks in space-time that may have formed during the earliest moments after the Big Bang. When the cosmos was still extremely hot and going through rapid phase transitions, the fabric of space may not have stitched together perfectly everywhere. These defects, if they exist, would be incredibly thin, thinner than an atom, but enormously dense. A single mile of cosmic string could weigh more than the Earth. Cosmic string could warp gravity around it like an invisible lens, bending light from distant objects. Some physicists think cosmic strings might have even helped seed the formation of galaxy clusters by creating gravitational distortions that pulled matter together early on. No cosmic string has been directly observed yet, but they remain a serious area of study in theoretical physics. Then there's dark flow. This is a controversial observation suggesting that large clusters of galaxies are all streaming in the same direction toward a point in the sky near the constellations Centaurus and Vela, at speeds between 600 and 1,000 kilometers per second. Some researchers think this motion could be caused by something massive pulling from beyond our observable horizon, possibly a structure or concentration of matter we'll never be able to see directly because its light will never reach us. Others argue dark flow is a statistical error or a fluke in the data. The speeds involved are enormous, hundreds of times faster than a bullet, and if the phenomenon is real, it means something beyond the edge of what we can see is exerting a measurable gravitational influence. As of 2026, the debate continues and new observations from the James Webb Space Telescope and other instruments are adding fresh data to both sides. Level 2, Hubble versus JWST. The Hubble telescope versus the James Webb Space Telescope. A huge amount of what we know about the large-scale universe comes from space telescopes, and the 2 biggest names are Hubble and JWST. NASA launched the Hubble Space Telescope in 1990, and it transformed our understanding of the cosmos. One of its most famous achievements was the Hubble Deep Field Image. Astronomers pointed the telescope at a seemingly empty, dark patch of sky about the size of a grain of sand held at arm's length, and held the shutter open for days. What came back was roughly 10,000 galaxies packed into that tiny area, with light from some of them having traveled over 12 billion years to reach us. That single image proved that the universe was far more crowded and ancient than most people had realized. It also meant that everywhere you look in the sky, no matter how empty it seems, there are thousands of galaxies hiding in the darkness. The universe has no truly empty spots. Hubble primarily sees invisible light, the same wavelengths our eyes detect. It did incredible work for over 3 decades, but it has its limits. Dust clouds block visible light, hiding whatever's behind them, and the most distant objects have their light stretched by the expansion of space into infrared wavelengths that Hubble simply can't capture well. JWST fills that gap. Launched in December 2021, the James Webb Space Telescope carries a 21-foot gold-coated mirror with roughly 6 times the collecting area of Hubble. It's designed to see in infrared, which lets it look through dust and detect light from the earliest galaxies that existed. The results have been stunning since day one. Take the cosmic cliffs in the Carina Nebula, about 7,600 light-years away. Hubble's image shows a hazy cloud-like edge. JWST's version of the same region reveals individual stars glittering across the frame and baby protostars still forming inside caverns of gas that were completely hidden before. Same object, same region of space, completely different level of detail. The Southern Ring Nebula is another good comparison. Hubble captured a glowing ring of gas around a dying star. JWST showed something Hubble missed entirely, revealing 2 stars at the center instead of 1. The dying star is shedding its outer layers while its companion star sculpts the expelled gas into an intricate pattern with 8 distinct lobes. In 2026, JWST confirmed galaxies at a redshift of 14.44, meaning we're seeing them just as they were 280 million years after the Big Bang. That pushes the boundary of cosmic dawn, the era when the first stars and galaxies started lighting up, even earlier than expected. The Helix Nebula offers another comparison. Hubble's visible light image shows a colorful ring of glowing gas. JWST's infrared view cuts through the outer layers and reveals dense knots of material, powerful stellar winds shaping the nebula from the inside out. Level 1, the Deep Field. One of the most powerful demonstrations of JWST's capability is the Deep Field comparison. The Hubble Ultra Deep Field image took 11 days of continuous exposure to capture its thousands of distant galaxies. JWST can achieve similar depth and detail in less than a single day, while also spotting galaxies that are fainter and farther away than anything Hubble could detect. Every tiny dot in a JWST Deep Field image is an entire galaxy containing billions of stars, and many of those galaxies are so far away that their light's been traveling for over 13 billion years to reach the telescope's mirror. Some of these galaxies existed when the universe was less than 5% of its current age. They were small, chaotic, and forming stars at an incredible rate. We're watching the universe build itself in real time, just 13 billion years after the fact. One more number to really land this. Light crossing our solar system from the sun to the outer edge of the Oort Cloud at about 100,000 astronomical units takes roughly 1.6 years. Here's the math. 1 astronomical unit equals about 8 light minutes. So 100,000 astronomical units is 800,000 light minutes. Divide that by 60, and you get about 13,333 light hours. Divide by 24, about 550 light days. Divide by 365, and you land at about 1.52 years. That means if the sun sent a postcard at the speed of light to the edge of our solar system, you'd wait about 18 months for it to arrive. And that's just our solar system. Scale that up to the Milky Way, and you're waiting 100,000 years. Scale it to the observable universe, and you'd need 46.5 billion years in any direction. Each new JWST image is basically a time machine, letting us look further back into the past and see more clearly than any instrument before it. From the red blood cell scale of Earth and Laniakea to the 93 billion light-year width of everything we can observe, we are unbelievably small. And through telescopes like Hubble and JWST, we keep mapping more of it every single year, finding things that formed at the very beginning and uncovering forces we still don't fully understand. The universe is vast and full of things waiting to be discovered.